Thanks. Yeah, so as you said, I work for Facebook. I actually work in Facebook Boston now. I moved there with my wife last August. So it's an interesting mix between the large company and the small startup environment. I did this during a hackamonth just as I was moving to Boston. So it's been incubating in the code for a little while we made sure that it was super stable, but it's now all available. So a good starting point would be to for why we had to worry about this is to look at the RocksDB architecture. So we have an active memtable. This is the in-memory place where we put all the data that we're adding, and then we also have to log it because durability. And then when we do reads, we pull from either the active memtable, the one that we're pulling from, or some of the ones that are kind of on their way to disk, or from LSMs that are on the disk. So the write path has to insert it into the active memtable, and it has to insert it into the log. So from a concurrency standpoint, on the read side, things are really good. Most of the stuff on the bottom is all immutable, so it's really easy to deal with concurrency. And it's not that hard to build a lock-free skip list, which is what we did for the memtable. So the readers are all lock-free. The write's not quite as good, though. So the original implementation was a single writer for the active memtable, and obviously the log is append only because that's what logs are. So the challenge here is to make it so that the write logic, like we're basically trying to extract as much concurrency as we can out of the write side. Given that we have a single log, the design that we inherited from LevelDB and what's served RocksDB well is just to have a single thread that's doing all of the writes. So obviously if you have multiple threads, you want all of them to be able to do the writes. We gather them all up into a single, the terminology is a little bit fuzzy because when a single thread merges things together, it calls them a write batch, and then when we merge multiple write batches together, we didn't want to call it a batch, so we called it a write batch group. So we have a group. So we gather all the pending groups. If there's multiple threads, then all of them get gathered up into a single thing. A single thread applies, writes all those to the write-ahead log, and then it goes ahead and does all of the memtable insertions. So if you have 40 threads that are trying to do your write, then the single thread is applying all 40 of those updates to the memtable. If a thread doesn't quite make the cut, then it has to wait. So it'll wait until because it didn't make the cut for the existing batch, it has to wait until the next batch. So we have a classic Amdahl's law situation here. We have parallel work and we have sequential work, and the sequential work means that no matter how many threads you throw at it, it doesn't really scale that well. In fact, it's even a little bit worse because if you put multiple threads, what ends up happening is that, like let's say you have two threads. One thread gets to do this write work, and then the other thread gets woken up when it's done, and it doesn't quite have enough time to join the next group. So you end up ping-ponging back and forth. So you end up finding that before all these changes, if you just had a single thread writing to RocksDB, that was probably actually your maximum throughput. You might break even again at maybe like 100 threads or something like that. So this is when then Igor told me like, okay, well, there's this big juicy Amdahl's law green section in the middle. Let's parallelize it and make everything great. We'll do a concurrent skip list. Concurrent adds to it. So I embarked on it, and the first thing I discovered was that wasn't actually the low-hanging fruit. So the actual low-hanging fruit was the work of gathering everything up and then distributing the results at the end. So this was all done under the main database mutex. So there was a lot of contention for the mutex when you were trying to assemble the batches, and then at the end, when you tried to wake everybody up and tell them that everything was done, they immediately woke up, and then they all contended to have a thundering herd on the lock. So most of them had to go and take another context switch again. So there's a lot of unnecessary context switching here. So before I did any work on the concurrent memtable stuff, I decided to work on making the write group construction and completion work better. So what I did is I built a lock-free way to join a write group and then point wake-ups for doing the wake-up when you're a particular, like if you were a follower and somebody else did the work for you, when they woke you up, you didn't have to take the main database mutex again. So I did this by, there's a little struct. It has in it the write payload. Every thread creates their own mutex and condition variable. This means we can do point wake-ups. And then we just have a compare and swap to link a new follower onto the front of the list. So this is great. People can join, they can join late. As long as you join just before the leader, like even after the leader's been chosen, you can still join the right group. So it helps avoid this ping-ponging issue. So there's an O of n squared problem hiding in here, which is, let's say you have a lot of work pending. The leader doesn't actually do all the work. It only does all the work up to a certain amount because it doesn't want to do like a 1 gigabyte write to the log. So it's possible that the leader doesn't actually wake up every pending follower. It only wakes up some at the end. But you'll notice that these arrows only go, I guess for you guys it goes that way. So that means that the leader has to start from the head of the list in order to find all the people to wake up. So if it only actually wakes up a couple and it has to keep retraversing the list as there's new leaders, we'd have O of n squared behavior. So what we do is we lazily fill links in the opposite direction. And this lets us essentially memoize the work done for doing wake-ups. It gets us back into O of n. So the reverse links are set lazily by the leader as it traverses across. So this is great. So now the followers never have to take the global mutex, like they can enqueue themselves in a lock-free fashion. The leader only has to take it once at the beginning. It doesn't have to use the global mutex at the end. And the group is chosen as late as possible. So we maximize the number of people that get to join the group. So this change is basically a strict improvement over the old one. Like it's never slower. It's always better. So we just put this in. There's no flags. It's been in there for a while. You're already benefiting from that. The result of this is that now when you go from 1 thread to 2 threads or 4 threads, it only slows down a tiny bit instead of slowing down a lot. So it's still not great, but at least it's not negative rate scalability. But it puts us in a situation where we can start to do better. So there was a paper from Yahoo, it was very, very interesting, where they basically built a concurrent memtable type, a memtable type that supported concurrent adds. And then they have some very impressive scalability numbers. They get basically pure linear scalability out of this thing. So our original idea was to try to take this and productionize it. But we ran into a few problems. So the first was, it was a completely separate memtable type that happened to be slower for the sequential case. So it led to an annoying, like, do you turn it on or not problem. Like if you turn it on, it might make you slower, it might make you faster. It's difficult to tell. RocksDB already has enough switches, so we didn't want to do that. The other problem was that they had completely rewrote the write path code. So that meant that all of the improvements that were made to scheduling compaction or throttling writes in order to balance the I/O, they were missing and there's a big software engineering cost to re-implementing them in a lock-free fashion. Also, while they chose to make their implementation serializable, it was not linearizable. You could, if you did a write and then immediately constructed a snapshot, the snapshot might not include the write, which is, it's the kind of thing that makes it so you can't just put it as a drop-in replacement. Like it's a long path to maturity and widespread use. So what we decided to do instead was to see if we can get, how far we can get towards that, reusing the existing write path and making it so that the parallelism is something that is only actually used when necessary. So there's no penalty for having it on. And we wanted to preserve the same write path, so we can preserve all the same maturity and improvements that keep being made to that code. So when I started this, I thought that the hard part was going to be the concurrent writes to the lock-free skip list. It's concurrent lock-free algorithms are generally difficult, especially in C++. Turned out that was actually by far the easiest part of the whole project. What actually was hard, well, there was the lock-free, like taking the low-hanging fruit so that we can actually get to the point where we can run things. We needed to have a scalable random number generator, which means that we have to switch to thread local, which changed the random number sequences when that meant some tests failed, so we had to go debug those. We needed a concurrent allocator that we can use that was high performance but didn't use extra memory. Because the existing code had been written in a sequential writer model, it had places where it communicated from one place to the other just by setting a field and then reading it later, which is not something you can do in a concurrent fashion. So we had to restructure some of that. Also, while I was in the middle of profiling all of this stuff, I found some sequential optimizations to do. So obviously, a sequential optimization helps everybody, so it made sense to do those first. And then finally, at the very end, the amount of work that we're actually parallelizing is pretty small. So we discovered that the the existing wake-up mechanism was kind of too heavyweight for us to fully capitalize. So we also had to do some work there. So all this stuff is included. Most of it's not even behind a switch. So because concurrent skip list, concurrent skip list is kind of the core of this whole thing, I wanted to explain what a skip list is. Actually, even why use a skip list? Why use a skip list instead of a B tree or a balanced tree structure? So a skip list is a randomized data structure. So what you do is you construct a linked list of all the nodes at a particular level. So if you look only at the very bottom of a skip list, it's just a linked list. You can start at the beginning and you can search along and you can find everything. And then when you're constructing your nodes, you randomly decide how tall this little ladder of pointers is at the top. If something is tall enough to participate in that particular level, then you link it in. And you structure this so that it looks kind of like a branching factor. So if you put your arrows in a slightly different direction, this would look like a tree structure. And this means that, in fact, we actually get O of log n search. So for example, let's say we're looking for the smallest element greater than or equal to y. We get to start at the top. So we basically proceed along a particular level until we discover that we're about to overshoot our target. And then we drop down. And if we keep repeating this, eventually we get down to the very bottom level where we can do an exact search. So all of these upper links are basically just working like a shortcut mechanism. They're not actually required in order to have the data structure do the right answer. They're just required for the data structure to do the answer in O of log n time. And there's no rebalancing or anything like that. This makes it very suitable as a concurrent data structure because balancing operations involve changing multiple links at the same time. And that's the essence of things that is hard to do in a lock-free fashion. So when we want to insert, let's say we have a new node, even though eventually this is going to be linked into all three levels, we don't actually have to link it. We can do just a single compare and swap to link it into the bottom level. And at this point, for all practical purposes, the node is actually part of the skip list. We don't have the O of log n behavior. We have to keep working our way up in order to preserve that. But each of those steps can be done independently. So this makes it very nice from a concurrency standpoint. And because each of these levels is independent, when we have a compare and swap failure, we get to just retry that particular level. The reason why I thought concurrent skip list might be difficult to implement here is because deletion is a lot harder. But it turns out RocksDB never deletes from the memtable, so that part was pretty easy. Okay, so what does it look like now? We have this picture is getting a little bit more busy, but we have the original housekeeping, which happens under the main global lock. Now we have a lock-free mechanism to gather up all the pending work. We still have to do the write-ahead log if you've got that enabled. If you don't have that enabled, then obviously it's faster. That section goes, this whole thing is not really to scale. Then we begin the parallel work. So we basically tell all the threads that we assign them their sequence numbers and tell them to go. And then everybody gets to do their own little piece of work on the memtable. But then because we want to preserve linearizability, we still want to make sure that we can't actually tell everybody that they're done until after we've advanced the sequence number, which this is the last step here is essentially the in-memory commit of all the writes. So when you're searching through the memtable, if you find something that has a sequence number that's larger than the sequence number of your snapshot, then you just ignore it. And this is the way that we can make things be visible atomically. So now we've got a little bit of back and forth here. There's extra synchronization rounds. So one of these synchronization rounds actually is not necessary. So all we have to do is keep track of when the last person finishes, and instead of having them tell the leader that the leader can now finish, they can just do the work of finishing themselves. We call this early exit. If you look in the code, you'll see the name early exit. Because we have these extra communication rounds, if you run the system as it's built here, what you'll find is that now almost all of these writers are finishing at about the same time, and this is kind of a worst case scenario for doing standard mutex plus condition variable wake-ups. So there's kind of a generic template here. You can either spin or you can put yourself to sleep in the operating system. Putting yourself to sleep in the operating system is pretty heavyweight. It depends on the operating system, but people they don't talk nanoseconds, they talk microseconds when they're counting it. Spinning is much faster, but it's selfish. You're not allowing Like there might be productive work to be done later. So there's this kind of game theory table that I put at the bottom. If you don't really try to spin and you didn't actually have to wait for very long, then it's bad. This is like limits your write scalability seriously. Like it'll being in that box is like a factor of 2 or factor of 3 drop in your total performance. If you spin for a little while and it's like a short wait, then everything is great. If it's a long wait and you didn't put yourself to sleep, like you spun for a long time, I didn't put bad here because it's actually not really bad if there's nothing else to do. It's more just selfish. You're taking a core that might or might not be able to do other productive work. So how do we fill in these question marks? In order to make this work well, all we really have to do is we have to make sure that we move ourselves from the selfish to the good block if we're taking resources away from everybody else. So the first thing to do is to make sure that we only spin if there's actually a good chance of spin success. So we put some counters in that are kind of exponentially weighted, whether or not spinning actually was okay last time. Then there's also like every once in a while it tries to spin for a while just to measure the duration. And then we have this other little question mark, which is, okay, is the OS run list pretty short? So how do you do that? Like, what system call do you call in order to find out that the OS's run queue is short? And how do you do that in a portable fashion? Because RocksDB runs in lots of places. We had an idea a while back. So you actually can interact with the run queue by calling sched yield or std this thread yield. What you're basically doing is you're saying run somebody else and then run me again later. So if you can either just call get rusage and count the number of context switches and find out whether or not somebody else actually ran. Because it turns out if you call sched yield and nobody else runs, it doesn't get counted against you. Or for even more portability and actually more performance, you just time it. You take the clock value before and the clock value after. If it comes back in 100 nanoseconds, then nobody else ran. If it comes back in a few microseconds, then somebody else ran. If it comes back very fast, we can basically extend our spinning for a pretty long period of time because we know that we're not actually hurting the rest of the world. If it comes back slow, then we should block right away. We use this in some of our other internal stuff that's in Folly. I don't know if anybody else has done this before. I use the word soft yield, or we use adaptive yield. Mark Callahan has done a bunch of numbers. I'm only going to include 2 of the slides to show you that it works. So this is if you have if you've turned off sync. And you'll notice that like the red line basically means that it doesn't matter how many threads you have, it doesn't get faster, and the blue line gets better. It doesn't get better as high as the number of cores, but we're getting into the like more than 1 million writes per second on the right side. And this is not even having any batching. So it turns out if you do batching, then you can get this number to go even further, and you can get the spread to go even wider. It actually even helps a lot when you're doing concurrent writes with syncing on commit enabled. So the first interesting thing here is that even without doing any sort of concurrent writes, we actually still get a performance benefit from having concurrent writers. And this is basically just if you have 20 threads that are all trying to write, and they all have sync on commit enabled, and they all get rolled into a single write batch group, then you only have to call sync once. So we're basically amortizing the syncs across. But there's actually still enough. There's still enough left in Amdahl's law that you can get a sizable performance improvement in this case. If you turn off your write-ahead log, then the numbers look even better. So this is my last slide. These options have actually been available since 4.4. We had a comment in there that said these are not stable yet, don't use them. But we took that comment out recently. The allow concurrent memtable write, it's not called use concurrent memtable write because it actually waits until the very last moment and decides whether it actually has multiple things to do before it decides whether to use one code path or the other. So if you don't actually have concurrent writes, then turning this on does nothing, nothing good or bad. And then the enable write thread adaptive yield switches it so that it tries to use this soft yield heuristic. In my micro benchmarks and benchmarks, I was never able to find any scenarios where these things hurt. But I'm only doing it on Linux on a particular class of machines, so it's possible that like we didn't want to just enable them by default until we get a broader experience from a wide range of platforms. But you should definitely try them if your writes are if you're doing multi-threaded writes.